Hey everyone, welcome to today's Explainer. Today, we're actually going to decode the invisible physical forces that shape our everyday lives. We're diving deep into the fascinating world of pressure, specifically focusing on the core concepts from Chapter 7. We live our entire lives completely submerged in fluids and interacting with solid surfaces, but we rarely stop to think about the immense, invisible weight acting on us literally every single second. So to kick things off, I've got a seriously counterintuitive puzzle for you that sets the stage perfectly. Okay, picture this. Who does more damage to a dance floor? A delicate dancer weighing about 600 newtons wearing stiletto heels, or a massive, multi-ton elephant? Now, your gut instinct probably screams that the huge, heavy elephant is going to cause absolute destruction, right? Well, physics actually tells us a completely different story, and the answer perfectly unlocks the real definition of pressure. See, what's really wild here is that pressure isn't just about weight. It is fundamentally about how much area that weight is spread across. The dancer is concentrating all of their downward force into that tiny, highly localized point of a stiletto heel. But the elephant, it has these massive, wide, flat feet that spread its tremendous weight out over a much, much larger surface.
So here is our roadmap for today's explainer. First, defining pressure. Second, solids, stilettos versus elephants. Third, liquid pressure and depth. Fourth, engineering for the deep. And fifth, the invisible weight of air.
All right, let's jump straight into Section 1, defining pressure. So, the crucial takeaway here is that pressure equals force divided by area. In physics, we write this as a lowercase p equals a capital F over a capital A. If you apply a force, measured in newtons, over an area measured in square meters, you get a unit called a Pascal. 1 Pascal is exactly 1 Newton per square meter. Basically, a massive force concentrated on a tiny area, that gives you incredibly high pressure. But take that exact same force and spread it out over a huge area, and your pressure drops dramatically. Which brings us to Section 2, solids, stilettos versus elephants. When we actually crunch the numbers from our 600 Newton dancer balancing on a single heel, which has an area of just 1 square centimeter, or 0.0001 square meters, things get pretty wild. You divide that 600 Newton force by that tiny fraction of a meter, and it turns out the dancer is exerting a staggering 6 million pascals of pressure. That is 6.0 megapascals. And here is the grand reveal. A standard dance floor surface actually breaks when it hits pressures over 5 million pascals, or 5.0 megapascals. Since our lightweight dancer is generating 6.0 megapascals, they will literally puncture and cause way more localized damage to the floor than a heavy elephant. The elephant's wide feet keep its ground pressure safely below that breaking point. Honestly, this is exactly why some dance halls strictly ban stiletto heels. Sorry, fashion lovers, but physics always wins. Okay, moving right along to Section 3, liquid pressure and depth. Imagine you dive underwater, kind of like a snorkeler. You immediately feel something completely different, don't you? You feel the pressure of the water pressing in on you equally from all sides. Unlike a solid that just pushes down on one spot, fluid pressure acts in every direction because all those fluid molecules are constantly bouncing around and colliding with your body. Plus, the deeper you go, the more water is stacked directly above you, pressing down with all its weight. This leads to a fascinating thought experiment. Think about this for a second. If you had a super long, reinforced plastic tube, could you just snorkel at the bottom of a deep lake? Could you just walk around 50 feet down, breathing air from the surface? Well, the answer is a resounding no, and this equation tells us exactly why. The change in pressure, delta P, equals the density of the fluid times the acceleration of gravity times the depth. Basically, liquid pressure is directly proportional to depth. As you go deeper, the crushing water pressure on your chest becomes so incredibly high that your chest muscles literally cannot expand your lungs to draw in air from that long tube. You'd just be physically trapped in this rigid cage of water pressure. That perfectly tees up Section 4, engineering for the deep. This is where human ingenuity really shines. At 600 meters down, marine exploring vehicles are facing pressure that's 61 times greater than at the surface. That is massive. To survive that, engineers design submarines with these thick, curved, spherical hulls because those shapes distribute that crushing force incredibly well. Their viewing windows are made of solid acrylic plastic, nearly 10 centimeters thick. And we see the exact same principle in architecture. Massive water dams are purposefully built to be much thicker at the absolute bottom than at the top, simply because the water pressure at that depth is the most extreme. But we don't just fight water pressure. We actually use this physics to our advantage. Take communities in Bhutan, for example. They build their water reservoirs high up on hills. By using that natural height, which is basically depth in reverse, and gravity, they create completely free liquid pressure. It's strong enough to push water all the way up into household rooftop storage tanks without needing a single electrical pump. It's just a brilliant, sustainable application of physics in everyday life. Finally, let's zoom out to Section 5, the invisible weight of air. For centuries, scientists have been obsessed with studying the atmosphere. This timeline takes us way back to Evangelista Torricelli in 1643. He invented the first mercury barometer, which proved, for the very first time, that air actually has weight. Then, jump to 1844, and Lucien Vitti invents the portable anerate barometer, using a sealed metal box and spring mechanism instead of liquid. These early leaps in understanding led directly to the vital tools we use all over the world today, like aviation altimeters and weather forecasting tech. Think about how a classic mercury barometer actually works. You've got a pool of liquid mercury and a glass tube with a vacuum at the top. The invisible atmosphere presses down on that open pool of mercury. And get this, that downward push is so strong that it forces the incredibly heavy liquid mercury up into the vacuum tube, holding it at a height of about 76 centimeters at sea level. Literally, a physical column of heavy metal is being propped up entirely by the invisible weight of the air around us. And that weight, it's constantly changing. By monitoring how much that invisible air weighs down on us from day to day, meteorologists can virtually predict the future. If atmospheric pressure is dropping, it usually means a storm or even a massive cyclone might be rolling in. A gradual increase in pressure forecasts fair, calm weather. But a sudden rise, that typically means fair weather, but with a good chance of rainfall. Our entire weather system is driven by these subtle shifts in the density and weight of the air. We almost always forget this, mostly because air feels so light and empty to us. But in reality, we are all basically deep-sea creatures living at the absolute bottom of a 10-kilometer deep ocean of atmospheric air. Just like that snorkeler submerged in water, you have an unimaginably massive column of gas stacked directly on top of your shoulders right now, being pulled down by Earth's gravity.
Which brings us to the end of our explainer, and I want to leave you with this final, kind of mind-bending thought. If a dancer in stilettos can shatter a floor, and if deep-sea submarines require thick acrylic and heavy steel to survive fluid pressure, why aren't you being instantly crushed by the 10 kilometers of heavy air pressing down on you right this second? Well, the incredible answer is that the liquids and tissues inside your own body are pushing back outward with the exact same immense pressure, balancing the scales perfectly to keep you alive. Take a moment to marvel at that internal engineering, and we'll see you in the next explainer.